Okay, so let me say today I'm going to talk about this field, which is in the intersection between set theory and group theory. And my main goal is to give an overview to present some of our recent results and some open questions. So let me start by saying that this will be joint work with Adam Clay. Okay. So I want to start with an outline of this talk. First, I'll be recall something about quotients of Polish spaces. Which is a research main trend in the descriptive set theory. Second, I want to talk about some area of group theory dealing with left orderable groups. And third part of the talk, I will talk about some interaction with geometric topology, and in particular with the theory of three manifolds. Okay, so let me start with the first part. I will mainly set up the context for this talk. We're interested in Polish spaces, so let X be a Polish space. And we always have G, a countable group that if you like, since we want also the group to be Polish, we can think about the group with the discrete topology. And in this talk, group will be acting on X in a continuous way. So the action will be continuous. And a main trend in the descriptive set theory is analyzing the complexity of the orbit equivalence relation induced by the action. And I will use this notation here. I will denote the orbit equivalence relation with R G on X. And this object is defined by saying that the 2 points of the space are related if and only if there is an element of the group sending X to Y. Okay, so in other terms, 2 points are related if they are in the same orbit. And the last notation that I want to introduce is I will often use X mod G just to denote the quotient of X modulo the corresponding equivalence relation. And we look at this quotient with a quotient Borel structure. So, and the Borel set of the quotient is defined as the set that if you take the union of all classes, you get a Borel set in the actual space X. Okay, so with this notation, a fundamental question. A fundamental question in descriptive set theory is whether the quotient arising from the action of G is standard space. Where standard mean either just a countable set with a discrete sigma algebra, or Borel isomorphic to the reals. And this kind of question has very old roots, which are actually not in set theories. Probably one of the first people wondering about this question was Ephros in the 60s. And more recent in descriptive set theory, there's a whole area caring about this question, originated by the initial paper of Harrington, Cakeris, and Louveau from the 90s. Okay, so the main tool that descriptive set theory offers to attack this question is the notion of smoothness. And what I mean by that is that we know that the quotient space is standard if and only if the orbit equivalence relation is smooth. And what it means here is that there exists an injection from the quotient into the reals that admits a Borel lifting map. So such that there exists a Borel map from X to R that makes the diagram commute. So let me finish the diagram. I'll call the injection phi, and I'll call the lifting map phi hat. And this is usually presented with the notion of Borel reducibility, if you guys are more familiar. This is the same as saying that R G on X is Borel reducible to the identity relation over the reals. Or if you prefer, the identity relation on any Polish space. Okay, so this is what I wanted to say about part one, to motivate the rest of my talk. Are there any questions? Okay. Okay, so for the second part, I'd like to introduce what is a left-orderable group. We say that a group G, and that will denote the operation with multiplication. We don't assume the group to be abelian. We say that G is left-orderable if there exists a strict total order on G, which is compatible with the operation. So such that for all x and y in G, we have that x is less than y, if and only if gx is less than gi for all g, x, y elements of the group. Okay, so there are different reasons to care about this notion. One of the reasons is that this is a natural notion that strengthens the property of being torsion-free. So if we have a group with, let me write this as an observation. Observation, G left-orderable implies that G is torsion-free. And the reason is because if you have an element of the group which has some torsion, such that its power gives the identity at some point, then the group cannot be left order. So suppose G different from the identity as order n. Okay, then what we have is that if G is a positive element, all its powers will be positive. So this cannot happen for torsion groups. So this is a natural notion that strengthens torsion freeness. One can indeed stratify the class of torsion-free groups in terms of order properties. If here we have torsion-free groups, contain is the class of left-orderable groups. An even smaller class that will show up later is the class of local indicable group. This is a class of group isolated by Higman. Local indicable is a local property, means that every finitely generated subgroup of G surjects onto the integers. And one can prove that every local indicable group is left orderable, and there is a characterization for this class in terms of orderings. And even something stronger is the class of bi-orderable groups, which is the class of groups that admits an order which is both left and right invariant. For example, every left-orderable abelian group is bi-orderable, because every order will be invariant both sides. And yes. So bi-orderable means there is an order which is invariant both sides. And for abelian groups, it's true that every order will be invariant both sides. Yeah. Okay. All right. And the other motivation, so if you like, this is motivation number one. There's a series of cool theorems that talk about left-orderable groups in terms of automorphism groups. And one that I found that I like to mention is this theorem. It's actually not very old. It's from 2001. Not very old, I said. By Goebel and Shalah. Is that the following are equivalent. One, G is left orderable, and second, G is isomorphic to the automorphism group of some group equipped with a bi-order. So if you like, left-orderable groups are a class of natural automorphism group that are arising as automorphism groups of order structures. Okay.
You're not requesting that the group is countable.
Here I'm not requesting that the group is countable. So maybe I should say here there's no, even here there's no need of countability for this definition, and here I'm not requesting that the group is countable. Yeah, thanks for observing this. No, it's not easy. You have to do some effort. You have to build a group that is. Well, if G is the automorphism group, yes, then you can define a left ordering. So it is certainly easy if H is countable, because you have an enumeration, and then you look. If you have two automorphisms, you look at the first element that is sent to different elements, so you can compare those with the order from the group. Yeah, Justin.
You really mean isomorphic?
I really mean isomorphic here. Yeah.
So basically the lexicographic. Okay, you one author H and then
Yeah.
the lexicographic order.
Yes, that works. That works.
But only if H is common.
Well, if you have a well order, then I can prove it. Yeah. Okay, are there any more questions?
One more question. So in solder, you don't require any kind of enumerability or anything?
No, this is the only condition that I require, this compatibility by left multiplication. Yeah, so there's there's no other condition on definability.
So I was wondering, because if you take some order of H, and it might produce some non-definable, but you don't care.
Yeah, it's still a left order on the group, yeah. Okay. Okay, I just want to mention this theorem because I found out it's a good motivation for this. I'm not saying that I'll be using it in the rest of the talk. Okay, so let's move forward. Need to move this. Okay, it's not falling down. Okay, so here what I'm interested in is what is called the space of left orderings, or space of left orders. Space of left orders. Okay, here let me stress that for G countable, we can define LO of G as the set of all subsets of G that are the positive cone of some left ordering on G. So what I mean here is that P is the set of elements in G that are positive for some left order less than on G. Okay, so this set lives in the power set of G, which can be considered as a topological space. Since G is countable, this guy is isomorphic to the Cantor space. And one can show that this set, as a subset of the Cantor space, is closed. Therefore, LO of G is a Polish space which is furthermore compact. Compact Polish space. Okay. And as I said at the beginning, we're interested in Polish spaces together with an action. Here, the action that we're considering is we have G acting on the space of its left orderings by conjugation. So since every element of L of G that I call P is just a set, GP is just the set of all conjugates of element in P. Or if you prefer, G is identified with a group of inner automorphism, and we let that group acting on LO of G. Well, if it is closed in the Cantor space, yes. The fact that it is closed, well, you can see by playing a little bit with the definition. So a positive cone for some left orderings is a sub-semigroup of G, that's a closed condition, that partition the non-trivial element of the groups into two parts, which is the positive part and the negative part. And one can write this just by using universal quantifiers. So it's the classical descriptive set theoretical argument using Tarski-Kuratowski algorithm to see the closure. Okay.
Does the positive cone uniquely detect the order, or you can have two orders?
Yes. So this is a good question. Let me write this because it may clarify the main picture. So the idea here is that every time we have a left ordering, we can somehow identify this with a positive cone, which is the set of positive elements of the group. If we have a suitable candidate for a positive cone that is a sub-semigroup and partition the non-trivial elements of the group into two parts, then we can somehow identify a unique left ordering. I don't know how to denote it, by saying that two elements, x is less than y, if and only if x inverse y is in G, is in P. Okay. All right. Are there more questions? Any more questions? Okay. So here I define this conjugacy action by conjugation. This is not something new in the literature. It's been studied by various people in group theory and dynamics, whose goal is he's studying the interplay between algebraic properties of G and dynamical properties of the action, of this conjugacy action. And the motivating question for this project appeared first in a monograph, on the right question here, by Derwan, Navas, and Rivas. And this monograph is called Groups, Orders, and Dynamics. So it goes by God, in God. They ask if we have some example of group such that the quotient space modulo the conjugacy action is non-standard. So let me write here, is there any left orderable group G such that LOG mod G is not standard. Yes. Non-standard, yeah, for us that we know descriptive set theory means non-smooth, exactly. So Maybe it wasn't clear to them, but this is the classical question that you can attack with discrete set theory. And the main tool that we use is generic ergodicity. Here, there is a proposition that plays a crucial role in several results that we have, so I might as well write it down. Proposition, which I think is due to folklore in the field. If we have a countable group G acting on X, with the assumption also that X is compact, then the induced orbit equivalence relation is smooth, implies that there exists a finite orbit. Basically, there exists a finite equivalence class. I want to say one more thing about this proposition. When we first write it down, the proof, there is a short proof. The short proof uses the Zorn's lemma. So if you look at our first paper, we wrote the proof down using the axiom of choice. But the full strength of the axiom of choice here is not needed by a Schoenfeld absoluteness argument. We just need the Borel, that codes for Borel sets are Pine-1-1, and this certainly happens with some weaker form of the axiom of choice. So for example, dependent choice is more than enough for what we want to prove. And I wanted to tell you that just because, you know, discrete set theory is the theory of definable sets. So somehow, if we use choice in the underlying machinery, this maybe could be viewed as some sort of weakness. But there's no need of choice here. Okay. One more this up. Okay, so now let me discuss some answers to this question, or the answer to this question. So this is the classical question that admits a yes or no answer, but it opens up further investigation about these objects. So the answer is yes to the question in a quite dramatic sense, meaning that we have several examples of group for which the quotient space LO G mod G is not standard. So let me draw this diagram. Here I'm writing groups for which the quotient space is standard. LO G mod G is not standard. So one situation for which the quotient space is obviously standard is for abelian groups. And the reason is just because conjugation doesn't do anything. So for those cases, the orbit equivalence relation is just the identity. So I write it G abelian. We could prove something stronger than this. If G is abelian by finite, then we also have that the quotient space is standard. This is one of our most recent results, 2023. And the reason is because if G is abelian by finite, which means that there is an abelian subgroup of finite index, then every equivalence class is finite. So the orbit equivalence relation is smooth. Okay, but now example for which the space is non-standard. So I was talking before in that diagram about local indicable group, which are the second subclass of torsion-free groups. we prove that L of G is non-standard if G is not locally indicable. And this was our result from 2022. And actually, it's quite easy to see that. The reason is because for this class of group, every class is infinite. Every orbit is infinite. So by taking the contrapositive of that proposition, the result follows quite easily. But also, one example for which LOG mod G is not standard is the free group. So for the free group Fn on n generators, nen 2 up to omega, we know in fact that the equivalence relation induced by the conjugacy action is universal. So being universal means being maximal among all countable Borel equivalence relations up to Borel reducibility. So actually for this class of group, the quotient space is as far as possible from being standard.
And this is locally indicable?
Yeah, the free group is locally indicable. It's in fact biorderable. So in the diagram over there, it sits on the very nice example of groups admitting biorders. Yeah. So in general, finding groups that are left orderable but not locally indicable, it's quite hard. I have an example here due to George Bergman, but there's really it's not highlighting of how a group of this sort looks like. But I'd like to move on to talk about another class of groups which are nice examples of left orderable groups for which this is not standard. So maybe I can, what should I raise? I can raise this. Okay, raise the title. I didn't mention this is also a 2022 result. Okay, so the third part of the outline was about free manifolds. So it turns out that an active area in which people are interested in left orderable groups is geometric topology. And the reason is that many fundamental groups of three manifolds are left orderable. And the three manifolds is just a manifold that locally looks like our universe. So one example for which the fundamental group is left orderable is the knot groups. Knot groups. So here, what is the idea? That if we have a knot, the knot is embedded into the sphere, and we can take the fundamental group of the complement, and that's the fundamental group associated to the knot. So if you like, never done this before. Okay. Should go here. Okay.
You can draw that picture quickly.
Well, but I couldn't. So please don't kick me out from this conference. Okay, so here, pi 1k.
Your pictures aren't as nice as yours.
Here, the fundamental group of the knot is indeed pi 1 of the solid sphere minus the interior of the knot. So for convenience, we think this is embedded into the sphere. Okay, so this is an example of compact closed manifolds. This is pretty nice. And it is well known that fundamental groups of knot are indeed local indicable. And as a consequence, they are left orderable. And the theorem here.
Would it change the fundamental group if one takes 13 instead of 6?
Well, the point is that topologists likes to work with the compact manifold. So in order to have compactness, you take the compactification of R3 and you imagine it embedded into the sphere. Yeah, thanks for the question. So here the theorem is this again 2023 for all knots which are non-trivial, which are different from the unknot, which is just the circle, no knot. LO of pi 1 k mod pi 1 k is not standard. So a great supply of left orderable group for which the quotient space is not standard come from geometric topology. And fortunately, we have I have to say that in the literature there are several techniques, several tricks to build left orderings on fundamental group of knots, and that's what was really relevant here. So how much time do I have? 5 minutes?
No, you have
More? Okay. Yeah. Is there any question, Justin?
Just to be clear, so the knot groups are always strippable?
Yeah, exactly. They are in fact local indicable. That's how you show that they are left orderable. Yeah. But there are other three manifolds for which the fundamental group is left orderable, so they're not the only examples. So I'm going to erase this, and I want to tell you a little bit more about this result, why we thought about knot group. Well, one of the reasons that Adam Clay has worked with knots before, but the other reason goes back to the techniques that we have to show that this sort of space is not standard. So there is a lemma saying that if G has a quotient, here I'm talking about quotient of G as a group that is left orderable and not local indicable, then ELO of G mod G is not standard. So this was just obtained by pushing forward that proposition over there and this result. And this seems to be useful for knots. It turns out that for all knot groups. There are various techniques called dance surgery. One can find a short exact sequence of groups. So here we have the quotient that we're interested in, such that this group here is not locally indicable. And also this group over here is the fundamental group of some other manifold that I will denote by Mn, called the dam filling of the knot group. So it looks like we're done, but quotients of left-orderable groups are not left-orderable in general. So there's a missing piece to apply our lemma. Okay, so what we observe is that using a very important conjecture on three manifolds, one can always conclude that G mod n is left-orderable. So there is a thing called
that all three groups, all fundamental groups of two manifolds are left.
Yes, I wanted to get there, and I also want to mention that first we observe that this follows from a conjecture called L-space conjecture, but in the end we could get rid of this as an extra assumption. So there is something called L-space conjecture. I'm not writing the conjecture because I don't think I have time, but this conjecture is saying that a fundamental group of a compact, close, connected three manifolds is left-orderable if and only if we have a certain condition on a form of homology, which is a topological invariant. It's called Higord-Floor homology. This is not important. But with L-space conjecture, I just want to point out that theorem from 2023 follows. And Matteo already made me say that we can get rid of the L-space conjecture. One can show this theorem somewhat directly. And the important thing here, again, is using the proposition about a finite orbit again. So that proposition, which is so general, so basic, actually finds many applications for knot groups. So let me just say what we do in our proof. Just the overview is that we find a closed invariant subset C of LO of pi 1k, very important, this set is non-empty, such that every equivalence class or every orbit in C is infinite. So we don't have smoothness if we consider the restriction to this closed subset, and therefore we cannot have smoothness for the all orbit equivalence relation defined on the whole space. Sorry for going over time. I'll stop here.
So thank you very much. Questions? Yes. Wait.
Yeah, just wanted to ask, is this also true for like two-dimensional manifolds, like surface groups? Are they also left-orderable, and do they also have the property of not?
Yeah, good question. That's true for all closed surface. So the fundamental group of every closed surface is left-orderable.
And is that also not the standard?
Oh, I see. Yeah, we have some results of about fundamental group of closed surfaces, and for many of them, one obtains universality, and the reason is that they contain the free group, and it sits in the group in a very special way. So somehow we can use the complexity of the free group as a lower bound for that. Thank you for your question.
Okay, I have three. First, a very nice talk.
Thank you.
I have three questions. So first, I'm kind of confused as to why, in what context did Duron, Navas, and Rivas ask the question? It's a sort of question you usually ask if you have some examples, but your chart seems to indicate that they didn't know anything when they asked the question, right? Because I mean, I guess maybe for abelian groups, but you would think, I would have assumed that they had lots of examples where they knew there was the quotient was standard, and it doesn't seem like that.
Yeah, so I don't know the one, but I've talked to Cristobal Rivas. He told me that it was Navas who asked that question. Okay. And what you're saying is basically true. It seems that they didn't know this arsenal of tools to attack their question.
Okay. So the next question is there any chance, so you removed the use of the L-space conjecture. Is there any chance that what you did says something about how to approach the L-space conjecture? I mean, or use some insight or something.
Yeah, of course, that would be very ambitious. The same construction that I mentioned here without giving any insight is called dense surgery. And you can do the same conjecture with a larger class of three manifolds. And for those classes, so for that class, the conjectural picture is again that L-space conjecture implies this version of theorem 2023. So of course, if one prove smoothness for some of those manifolds in the class, one can disprove the L-space conjecture. But I have to be honest, it seems out of reach, although the picture is very clear. The picture connecting these two areas is very clear, but it seems out of reach at the moment.
Okay. And finally, I feel like I have an obligation to ask the next question just because everyone's I'm sure there are some people that would expect me to ask this, is what about Thompson's group?
It's a very interesting example. So here I didn't mention every group that we have considered. We started working more recently about groups that are amenable. So my conjecture is that the only group for which the space is standard is groups that are abelian bifinite. At least these are the only examples that we have. It seems still very challenging to prove that. We have some example of solvable group for which the quotient space is not smooth, like Bamslack solitar. That's something very recent that hasn't been written up yet. So for Thompson group, I expect having a space that is not standard, but proving hyperfiniteness in this context is very hard, extremely hard.
Yes.
So there is a way from going from the fundamental groups to this left order of groups. Do you have a way back for some classes? So if you have you can find a knot that get the fundamental group, the manifold is the group.
Yeah, I'm not sure of any. So you usually work with manifolds for which you have already computed the fundamental group and you know what the fundamental group is. So going the other way seems a little bit unclear to me. I'm not sure if that's what. Yeah, that's addresses your question.
Groups, left order or groups that tells you this can be the fundamental group of a manifold.
Yeah, I'm not sure. I don't have anything on top of my head on that respect.
So can there be a group for which there is a generic linear order, meaning that comeager orbit in this action?
I think it could be. So if the space is perfect, no, because the classes are countable. But the space of left ordering is not always perfect. So that's a good question. Does it make any sense what I say? I think, yeah, I don't know any examples.
Okay, any more questions? Okay, so thank you very much again.
Thank you.